I'm going to invite our next speaker, Mohammad Akhlaghi. I'm sorry if I pronounce it weird. My name is also very difficult to pronounce, so I know how it works. So what's not on this slide, because this is presenting him and his institution, which is a very important Spanish institution, is that Mohammed is one of our ambassadors.
Yes.
So not the first ambassador, but almost the second ambassador. No,
really?
The third ambassador. Sorry,
really?
third ambassador.
Okay.
And so he will present to us also another idea of how implementing software heritage in workflows. So go ahead. I know you have lots of slides.
Yes, yes. Okay, thank you very much. I'll just start my timer. Okay, so thank you very much, everyone. It's a real pleasure to be here. I've been in touch with Roberto and Marane in the last few years, and it's been really productive. So the basic idea behind this talk is that until now, ever since in the morning and until now, in talks, usually software heritage has been discussed in the context of number crunching software, right? I mean, like the software, the low-level software that the high-level research, let's say, at least in research, depends on, right? So for example, Jose was showing the plot for Matplotlib and showing that the research software is just a thin layer on top of it. So over here, I'm going to show how you can actually use software heritage for the whole research project, even that thin layer, and even the LaTeX source, even how you build the plots, and effectively the whole, let's say, workflow of a project, including the software, of course, the low-level and high-level software. So there's also a paper that just wanted, because opening links is important. I hope I can open links during the talk. Okay, good. Is it shared on Zoom?
Yes, it is shared on Zoom.
Okay, great. So for example, like let me just go to this this paper because it's important. You'll be impressed, I hope. So the second author, Raul, is also here today of this project. And so look, in the abstract, we have the software heritage ID in the abstract, and you can actually click on it, and it will take you. So this will take you directly to software heritage, and in software heritage, it's not, as I said, it's not just the software; it's also the paper.tech. So it has look like everything. I mean, and now I'll show you in the slides I hope it's been in a useful way, but it's not so effectively. I'm saying that it's not just code, as Roberto was really nicely emphasizing today. I don't see him here. Is he?
No,
yeah. So like he was focusing on the comments in the code. We don't just have to rely on comments. We can have a full narrative of the project. So so let's go on to see what this proposed method is. Okay, so when we think of a workflow, right, we think of yeah, I have some software, I have my data, and then I build my software, and then I run my software, and boom, I have my paper, right? So then this is how a paper comes out. But then, as we all know, there's many questions. How was the software built? Where did the data come from? So this was just the previous talk that they were talking about connecting data and analysis and everything together in one thing. And more importantly, how the software will run on the data. And finally, yeah, the actual text of the paper, the research. So it's not doesn't just have to be research like a data release report or a you know many different. Well, anything ultimately comes up to you want to make even a web page to like announce a new version of your like high level software. So because well, ultimately science is a really tricky business, and just simply archiving the let's say number crunching code is not enough. We really need the high level commands, that thin layer that really you know connects all of these number crunching algorithms together to generate the final plot, because that's what people read. The final plot is what people. We should really kind of be able to connect the final plot in the paper to the core like loop in the number crunching algorithm. And well, as you know, there's a big reproducibility crisis. I'll just skip this. So I don't have time. I just have 10 minutes left. The basic idea behind what we proposed, what we built in the last, so this was built really organically. We didn't set up to build this. We wanted to do our astronomy. So I'm an astronomer. Raul is an astronomer. I never had a single official course in computer science. It was just astronomy. But I wanted to do my astronomy properly. So I spent most of my PhD studying computer science and algorithms and programming and software design. And this kind of blends in with the package I wrote for GNU astronomy utilities, and I submitted it to GNU, so they were really helpful because they referee the code. So it was really great for me as a complete outsider to software. And then I tried to implement it into the workflow and the final papers that we were publishing. So the basic idea is that the project should be complete. You should be able to run the project with a minimal Unix-like system. Now over here I called it POSIX. Well, POSIX is not too well defined, let's say. So let's just say minimal Unix-like operating system. It should not require root access. That's the primary reason. I mean, we were really impressed by Geeks and Neats. But because it needed root access, we couldn't install them on our institute servers. I was really planning to use Nix and Geeks for the software packaging part, but I couldn't. Our institute, well, I tried to talk to them. They won't allow installing anything. They won't give me root permission. So then it should be able to run non-interactively. It should be able to run if the data are there without internet. It should be modular. It should be plain text. No, no fancy graphic user interface. And it should be minimally complex. It should be all the inputs and outputs. So the data, when they arrive and when they get going to the plot, they should be verifiable. And of course, as we all know, they should be free software. So, so the first part is about the package management part. So in package management, so just in package management, so first we'll just look in this top left part of the plot, and so the whole thing is designed in Make, from the package management to the analysis, to running later, to build the PDF of your paper. Everything is done in Make. So effectively, we build the whole software environment, including GCC, and we're trying to work on the C library to include it also. So it builds from GCC. It even builds GCC and comes up effectively and builds the whole, let's say, environment. So right now, it's the only part that it links to the host operating system is through the C library in the kernel. But we're trying to work on that C library part as well. So build everything. Effectively, it's you see over here, I've like highlighted a few software and their versions. So you see all the software used in the project, along with their versions, is a plain text file that can be on the software archive in software heritage. So I'll show you this file in software heritage for the project I'll show. So this is the famous plot that he also showed. Thank you very much, software heritage team, to make this plot. So this paper was really good. Many people opened their eyes when I showed this in the astronomy community, because matplotlib is also heavily used, and many people don't know. It's a wonderful plot. Thank you. Okay, so you see, it builds everything. It builds bash, make, lscp. We don't rely on the host operating system. And that's because, well, for our research, like we were working on this cluster in our institute, some of our data was in another institute, and their make dir changed. The behavior was different. And at first you think, you just read it, but then when it causes a crash in your pipeline, you say, I'm not going to waste my time anymore. I'm just going to install core utils and and just have my own mkdir. So yeah, because it doesn't need root permissions, when you install it on a new server, you don't have to spend hours and hours and days sometimes continuing with the HPC maintainers that please install this software, and then you spend hours, and then all these issues. So yeah, and everything is built in one directory, so it doesn't need, you can have multiple directories for multiple projects, and they won't conflict. And again, everything is in plain text. So for example, because we build the software ourselves, in the script to build the software, we actually give you BibTeX citation, now hopefully we'll include the BibLaTeX software heritage as well. Not hopefully, we will do that. I've been in touch with you about it. This paragraph is generated automatically. In this paper, we didn't write this paragraph. This paragraph and all the citations in it and the versions and names of software are generated automatically as a LaTeX macro. So as like a user of the system, you just have to write one line like backslash, like software link, I don't know the name of the macro. You just write that single macro line, and this will pop up in your PDF. You know, with all the citations, all the versions and names of the necessary software in your project. Well, but as we said, research is not just the software. Where do the data come from? So there's a special file again in the repository, and it's called inputs.nk by default. Well, now I think it's on. So for every data set, every external data set that's used in the project, look, you have the URL, you have the name of the file, and you have the MD5 checksum, the verification of the input. So every input that it downloads, immediately will check the MD5 checksum. And if the MD5 checksum of the input does not match, so like if the database has updated their data without telling you, or changing the URL of the data, the pipeline is going to crash. It's going to stop. It's going to say, be careful. The input is not what the authors wanted. I'm not going to continue. Now, as the user, you have godlike power, so you can say ignore, but at least it's going to tell you. Then you have the most important part, how you run the software on the data and the software after each other. So again, as I said, everything is done in Make. And the reason we chose Make was that, well, it's 40 years it's being developed and it's still being developed. The whole operating system is built in Make. It's going to be developed in the foreseeable future until, I don't know, some new revolution in computer science comes and operating systems change. But essentially, as you all know, everything we use in our operating system is built by Make, and it's being developed, it's being improved, it's really fast, it's parallel. Well, things like the Linux kernel are built in Make. Well, over here, the project, essentially, instead of having .c and .o files, you know, in C compilation, we actually have data files. So one data file has dependency data files, and then you just effectively run them, and you're able to create your full workflow. Now I'll visually show this later. And finally, the text, the narrative, which is the most important part. And this is like historically, it was the first aspect of how I started to work on this. I was writing my paper for my PhD thesis, and every time I made a change, I had to go over the whole paper and update every single number. And I'm sure most of you have gone through this frustration. So at one point I said, that's enough for me. Look here. This is the PDF of the paper, and this is the LaTeX source. Look, the three numbers at the end of this paragraph in the PDF are not numbers in the LaTeX source. They're LaTeX macros. And then all of these macros come from a single file called text macros, and you see here are the three numbers. Every number in the paper is a LaTeX macro. And then this macro is generated at the exact moment, this particular data set that I'm talking about in the paragraph, at that exact same moment that data set is created, the macro is written. So you see over here, it's just a loop. So all three of those are generated by a single script. And so you see, this is how you just change one step of the analysis. You press enter and it's Make. So it's only going to find the dependencies, only going to run those dependencies, and it's going to update your numbers. You know, in the PDF, you're going to have a new number next time. So as a demonstration, let me show you. So, you know, in Make, so we think from the end, right? So what's the ultimate goal of all of us when we're writing a paper? Paper.pdf, right? So we want paper.pdf. Well, where does paper.pdf come from? It comes from paper.text. So the green files here are files that you write by hand that go into software heritage. The blue ones are the files that are created automatically. So your paper essentially needs these two files. So the full bibliography of the paper is also put on software heritage. And then, so this project.text is the file that has all those macros that go into creating the numbers and plots and tables of the paper. But before we go into the analysis, everything is verified. So the user also at the end, so the moment you want to publish your paper, it also makes a checksum of all of the files, all of the final LaTeX macro files that go into this step. So in this verify step, we check all of those. And then, so now let's look at how the data come in. So look, like over here, we want to generate this plot. This plot here, this is a plot from a paper that they were citing how many papers, the fraction of papers that have cited software. And so now we're going on. So then how does this verify? Get its input. So it gets its input from demoplots.tech. So it's a LaTeX source. I made the plot with LaTeX. And then where does this come from? Tools per year.tech. This was the column in that thing. And where does this come from? The full table that had many columns. And where does this come from? The XLS file that I downloaded. And where did I download that from? The handwritten inputs.mk file that had the URL and the checksum. So all of these, you see the full lineage of the data from a handwritten file to the final PDF is now here. Okay, I'll just try to rush and finish my 15 minutes. And okay, so you see this is easily expandable. So like over here, in the paper, in the text of the paper, like I've used a number. I've said like in the year 1985, like there was this many fractions. So this number actually comes here. So if you go to the paper source, change this from 1996 to 1998 and press enter, and the PDF is going to show a new number for that. And you can easily expand this because it's all modular and easily expandable. And the final aspect is that since it's plain text, the whole thing is in one Git project. And this is how essentially Maneage is defined. Today, we have one set of answers to these questions. Tomorrow, we have another, we update. And Maneage is effectively, it's managing data lineage. So that's the data lineage in time and data. So Maneage is a Git branch, and then you branch off. So it's just to start your project, you clone Maneage, and then you create your own main branch, your master branch, and you start editing. And the important thing is that in each commit, you have everything. So like if in the middle of this, you update the version of your software, that also gets updated. And you go on. The best thing, when you publish your paper, the Git hash is also given as a LaTeX macro, and that gets printed into the abstract beside the software heritage ID of the thing, and your paper gets verified. So then, for example, over here, these are two papers with Git hashes and the things. Okay, now let me show you the software heritage ID. So because it's plain text, we also put the source, the whole thing on archive, but well, archive is just a snapshot. It's nothing. But with software heritage, we can actually, as you saw before, you see everything is here. So like I even put the peer review. So you can actually go and see the comments from the referees. I don't know if any of them are here. They were anonymous. So I got permission from the editor. So the editor allowed me to share. So you see in software heritage, you even have the referee report. Well, besides the referee reports, you can come here. In tech, you can see the source of every single plot that we made. If you come here, you can see the exact PGF plots source of how the LaTeX was built. And you have the full history from the moment we wrote the first paragraph. And imagine like this with what you can do with software heritage. And all of the projects will branch from a single core Maneage branch. And the analysis and the text are blended. So with the history, like when 1,000 papers write this, imagine you can blend in how they change their text based on how they change their code or the opposite, and things like that. So the whole thing is on software heritage, and we actually use this as well beside the abstract that you saw before. I'll finish here. Sorry, it's taken a little too long. But besides the abstract, we also have the, come on. So it's just 3 minutes over time, please. Excuse me. Come on, go down. Okay. So I'm having trouble scrolling.
I think it's so interesting.
Yeah.
That's why.
Great. So look, like for example, under this listing of the paper, when I click on this, I had to talk a lot with the publication editor of the journal to fix the software heritage issue thing. But they were really kind and they worked a lot. They helped a lot and they finally done it. So look, I just clicked on that link. And so in the link, this is based on Roberto's suggestion. The software heritage ID under the figure, it's just the core, the low level, the file software heritage ID. But then when I go on it, I don't know if it shows the link. See the link down here? had the full concept of the software. So when you click on it, it actually takes you and it actually has all the metadata, let's say, of the file, which project it belongs to, and all the other contexts that are necessary. And you see, this is how, and we're actually using it in our science papers as well. So there's more papers that have software heritage ID. There are already a few more published and many more are coming. Thank you very much. Sorry, I got 4 minutes late.
We talked a lot about magic today, and this looks like real magic. So really, yeah, that's impressive. Thank you, Mohammad, for coming here and presenting that. I'm sorry, with you too. I'm not going to allow any questions, even though I know there are some curious here about Maneage. You should pick his brains afterwards.